I'd like to do a few more examples with you that involve e. And let's start by graphing an exponential function with a base of e. So we're looking at this one, sketch the graph. So when you move to calculus, the expectation will be that you could sketch a function like this in just a few seconds. So let's make sure that you can do that. Remember that an exponential with a base that is bigger than 1 looks like this. So that's y equals 3 to the x, or 2 to the x, or 17 to the x. And the base determines how rapidly it increases. So we could consider this to be a rough sketch of y equals e to the x. Remember, the asymptote is along this x-axis. But as soon as we have a negative x instead of an x, remember that means the graph reflects across the y-axis. So our graph would look like this. It would go through 1 right here. And I'm going to just grab a pencil for a moment, and I'll tell you why in just a minute. It's asymptotic right here. And depending on the nature of why you needed the exponential function graphed, you could consider it done. But if it needed to be a little more refined than this, maybe the shape isn't perfect or close to perfect, and you wanted to plot a point, you could do that and make it look a little bit better. For example, for this particular problem, maybe I have it a little bit too steep. We could plot the point -1, for example, the x value -1, pop the -1 into the function, and if you put in -1, you'd have e to the +1 power, and we know e is about 2.7, so there's 1, that would be 2, this would be 3 right here. So at -1, it would be at about 2.7. So my curve is a little bit off, and I could do a better job for this particular one. But often, as I said, a rough sketch is all you need. But plot a point or two if it needs to be just a little bit more precise. So I have this point at -1, it's up here at e, which is about 2.7. Similarly, I could put in the value 1, and I would get 1 over e, or close to a third. And when I draw my curve, it now looks, whoops, made it a little bit funny there, coming down this direction. Let's do another one. Let's graph f of x equals e to the x plus 2. Again, we know the base graph looks something like this. Let's just come up with our rough sketch. We know that a +2 here represents a vertical shift. So I'm going to move the exponential graph up 2 units. So instead of having the asymptote on the x-axis, I'm going to put the asymptote right here at 2. I'm going to put it in with a dashed line so that would be clear. Instead of having my y-intercept at 1, it is also moved up 2 units, so it's now here at 3. And let me label that. So those are key points with respect to this graph. The fact that there's an asymptote at 2 and the y-intercept is 3, and then I can draw my curve. And again, plot points if it needed to be a little bit more refined. Let's do something else. Let's do a problem that looks like this. Another exponential type problem. I'm not asking for a graph this time, but it's just a problem that gets modeled by an exponential function. Suppose that in a specific culture, the number of bacteria present after T hours is given by this equation. Now, before we proceed, consider whether the number of bacteria are getting larger or getting smaller. We know that the base is bigger than 1, and as we put in positive t values, this exponent is going to be positive. We know that the curve is going to be increasing. So whatever this population is, we know that the smallest value it will be is at time 0. I'm going to assume for the purposes of this problem that negative values are not acceptable to substitute in for time, because notice it says here how many bacteria are present initially, and generally that means we're talking about time 0. So for this particular problem, the assumption is that time, the domain for this function will be 0 to infinity, so to speak, although that probably wouldn't be a good model at 2 trillion hours. But in any case, for this particular problem, we'll assume we'll put in positive values for t. So let's start with the number of bacteria initially. Let's put in 0, and we have 1,000 e to the 0.029 times 0. Now we don't even need a calculator for this one. We know 0 times 0.029 is just 0. So we would have 1,000 times e to the 0 power. But we know e to the 0 power is just 1. So 1 times 1,000 is 1,000. So how many bacteria are present initially? 1,000. And now let's do part B. How many bacteria are present after 6 hours? So we're going to substitute 6 into this function. So n of 6. And this is just a nice calculator problem. E to the 0.029 times 6. So grab your calculator and we'll punch that in. We have 1,000 times e to the 0.029 times 6. And I get about 1,190. So after 6 hours, if the culture is growing according to this model, there would be 1,190 bacteria present 6 hours later. Let's do another problem. Suppose that a radioactive substance decays in such a way that the amount of mass remaining after t years is given by this equation, where m is measured in grams. So time is in years and m is measured in grams. And notice, even though it says decays, which implies it's getting smaller, notice the base is bigger than 1, but we have this negative value. So as we put in time values that are positive, we're raising e to negative exponents, and we'll see that it's going to be decreasing as time passes. So let's find the mass initially. So we're going to put in 0. So we have 50 e to the negative 0.13 times 0. And if we do this calculation, again, as with the previous one, we'd have e to the 0, which is 1, so we would get 50. So I have 50 grams of the substance present initially. What's the mass of the radioactive substance 10 years later? Let's substitute in 10, and we'll do the calculation. Remember, we expect it to be something smaller than 50 because we know we have a graph. If you were to graph it, that would be decreasing as time passes. And it's because of that negative right there. So let's pop in 10. We have 50 e to the negative 0.13 times 10. Make sure on your calculator that you put in this entire quantity as the exponent on your E. So in other words, I'm saying when you punch into your calculator, it's e to the negative 0.13 times 10. You'd want parentheses around that entire exponent. So let me punch it in, see what I come up with. You do the same. And I get about 13.6. I'll just round to the nearest tenth. So after 10 years, if the radioactive substance decays according to this model, we would expect there to be 13.6 grams remaining. Let's do one last problem. This one looks a little bit different. Suppose that the population of fish in a specific lake is given by this equation, whereas the previous problems sort of have unrestricted growth or decay. This one does not. If you throw fish in a lake, they can't just grow forever. They're constrained by their environment. And when you see that kind of thing happening, you see equations that look like this. If you're interested in this kind of an equation, you can look up logistic growth models, and you'll see lots of real life problems where things are constrained. They can't just grow exponentially forever. So let's just practice using this equation. I'm going to put in times 0. So we'll have n of 0 equals 2800 divided by 0.3 plus 13.7 e to the negative 0.15 times 0. Now we could grab our calculator, but I think it'd be kind of fun to just do this one by hand. This again will be e to the 0 power, and we know e to the 0 power is just 1. So we would have 2800 divided by 0.3 plus 13.7 times 1. I ran out of space, so I'm going to have to move here to the right, but that's 2800 divided by 14. And we know that that's equal to 200. So initially, whatever time they say is time 0 at the beginning of this problem, that could be today or 3 years ago, whatever is determined to be time 0, there are 200 fish in the lake. Now let's talk about the fish population 12 years later. We're going to pop a 12 into the equation. We have 2800 divided by 0.3 plus 13.7 e to the negative 0.15 times 12. Grab your calculator and punch this one in. Keep in mind you'll need parentheses around this denominator if you punch it in the way that it looks here. And of course, it depends on the way your calculator works. There are a variety of calculators and a variety of ways to put this in, but for many calculators, you would need to put parentheses here. But practice with your calculator. I'll give you a moment to punch that in, see what you come up with. I will punch it in here as well. Did you get where my value go? Did you get 1092? So if the population of fish grows according to this model, in 12 years we'll have grown from 200 fish to 1092 fish. So I hope you'll go practice working with some problems that involve doing some graphing and a few word problems.